Welcome back to the deep dive. I have this long-standing fascination with project schedules. You know, the kind I mean, right?
The ones that look like a work of art.
Exactly. Pure mathematical elegance. A Gantt chart that's so perfectly optimized, it promises the fastest possible delivery date down to the minute.
And if you've been in this world for any length of time, you know the paradox. Those beautiful schedules are often just blueprints for a disaster.
They fail spectacularly the moment they hit the real world.
The moment physics gets involved.
That's it. That's the crisis of the beautiful but impossible schedule. It looks flawless on a screen, but you try to factor in something real, like, I don't know, the delivery time for a specific material, or the fact that concrete has to set.
And the whole thing just collapses. The elegant math can't handle it.
So today, that's what you're doing.
Yeah.
A really critical deep dive into project logistics to figure out exactly where that failure point is.
And our focus is going to be on the most advanced methods. We're talking about resource-constrained project scheduling, or RCPSP. This isn't a beginner's guide. We're dissecting the root cause of failure in these really high-precision models.
Our mission is, well, it's very specific. We want to identify why a single conceptual decision, how you classify the very nature or the ontology of a resource, is what decides if your schedule is an executable plan.
Or, as you said, a work of fiction, a logistical fantasy. We're getting right into the weeds on the difference between storable and non-storable resources.
And this isn't just academic, is it?
Not at all. I mean, if a project goes off the rails, the failure is almost never the algorithm's calculation. It's the planner's initial assumption. It's that conceptual error right at the start. A powerful scheduling engine is only as good as the physics you tell it to obey.
Which I think brings us to our core idea for today. The provocation, really. Let's call it the golden rule.
I like that.
Modeling a resource incorrectly is actually worse than not modeling it at all.
That's absolutely it. That is the ultimate test for a planner. If you get the resource physics wrong, say you treat a time-bound opportunity as if it were a pile of bricks, the schedule you get back is, well, it's dangerous.
How so?
Because it gives you this false confidence. It's a coherent, mathematically perfect answer. But for a world that doesn't exist, you end up trusting dates that reality simply cannot and will not deliver.
And our goal today is to help get rid of that fundamental blind spot.
Exactly.
Okay, let's unpack this. I think we need to trace the evolution of scheduling logic to see where these dangerous assumptions creep in.
Sounds good. Let's start from the beginning.
To really get why correct RCPSP modeling is so vital, we have to look at the baseline, right? Most projects still operate in.
We do. We need to set up a comparison. There are really 3 different modeling scenarios that define the physics of a schedule.
Okay, what are they?
You start at the bottom with the foundation of everything, the critical path method, or CPM. That's the simplest, but honestly, it's often the most misleading. Then you level up to RCPSP, but even there you have 2 flavors. One where you treat a resource as storable, and one where you correctly model it as non-storable.
So let's start with scenario 1, CPM. It's taught everywhere, it's used everywhere, but our source material is pretty clear that it has this fundamental inherent flaw.
It does.
What is CPM actually optimizing for, and what is it just ignoring?
CPM is designed for one thing and one thing only: sequencing and duration. It looks at the technological dependencies between tasks.
So you can't put the roof on until the walls are up.
Exactly. And it operates on a single driving principle: push every activity to start as early as possible based on when the preceding task finishes. It gives you the shortest theoretical timeline, mathematically.
But the key word there is theoretical.
It is, because to achieve that speed, it has to explicitly ignore the logistical physics of the real world. It ignores resources, materials, and any real constraints.
It sounds like one of those high school physics problems, you know, assume a vacuum and a frictionless plane.
That is the perfect analogy. The assumption baked into CPM is profoundly dangerous. It assumes that resources exist by definition the very second they're needed.
So if my schedule says I need 50 tons of gravel on Monday,
CPM just assumes 50 tons of gravel materializes on your site on Monday. It anticipates the consumption, but it never, ever checks if the quarry can produce it, if the trucks can deliver it, or if you even have a place to put it.
So you get this beautifully short 6-month schedule that's based on completely impossible resource availability, a plan that requires things to just pop into existence.
Absolutely. Think about a big infrastructure project. CPM might schedule 3 massive simultaneous concrete pours because the formwork for all 3 is technically finished.
Right.
It assumes the concrete plant has infinite capacity, or that you have enough trucks, or that the single road to the site won't be a bottleneck. The second you introduce reality like, say, a daily limit of 200 cubic meters of concrete, that 6-month CPM schedule is immediately invalid.
It literally sets the project up to fail before a shovel even hits the dirt.
Because the entire premise of that short duration is a logistics chain that doesn't exist.
Which I guess is why we have RCPSP.
Exactly. We bring in resource-constrained project scheduling to fix that specific flaw. RCPSP says, hold on, resources are finite. It enforces the rule. You can't start this activity until the resource is actually available. It's supposed to eliminate those deficits.
But just using RCPSP isn't a magic bullet, is it? Because we can still feed the engine the wrong information.
That's the crux of it. RCPSP is an incredibly powerful optimization tool, but it needs the human planner to correctly define the nature of the constraints. If we misclassify a resource, we're just running a much more complicated simulation of that same non-existent world.
The math will balance, but the project will still fail.
Yes. That initial definition, the resource ontology, is the single most critical starting point.
Okay. Let's get into those definitions then.
Yeah.
This feels like where the job shifts from just math to, well, logistics physics.
It is. And we need to be really clear that these are operational definitions. They're designed to tell the algorithm how to behave.
All about governing the math.
Precisely. Let's start with the one that gives us flexibility. The storable material resource.
Okay.
This is the one that aligns perfectly with how we think about traditional inventory. It's any material that you can produce or deliver, pile up in a warehouse or a staging area, and then use it later without it, going bad or losing performance.
So we're talking about the basics. Piles of sand, gravel, structural steel beams, pre-made pipes, electrical components, things that can sit around for a while.
Exactly right. And when you define a resource as storable, the algorithm uses what's called stock balance logic. If your daily capacity is 100 units and you only use 50.
The other 50 roll over to the next day.
Correct. That accumulated stock balance gets added to tomorrow's capacity. So on Tuesday, the model thinks you have today's 100 plus yesterday's leftover 50. And that logic is perfectly sound, but only for storable inventory. It's how we manage buffers and smooth out the supply chain.
Which brings us to the resource that breaks that entire model, the non-storable material resource.
This is the critical distinction. By definition, a non-storable resource is one where unused capacity from today cannot be turned into a useful balance for tomorrow.
The opportunity is time-bound.
Perfectly put. Availability resets. The unused portion from today just vanishes. It's an opportunity cost.
And within that non-storable category, there's a really instructive subgroup, the perishable resource.
Right. A perishable resource is non-storable for a very specific reason. Its technical properties are tied to a stopwatch. If you don't use it in time, it degrades, it loses performance, or it becomes totally useless.
And the classic teaching example, the one that perfectly shows this error, is fresh concrete.
Concrete is the absolute quintessential perishable material. You make it, you deliver it, and you have to place it and finish it while it's still workable before it starts to cure.
So if you produce 100 cubic meters today, but your crew only pours 50.
The other 50 don't get saved for tomorrow. They harden in the truck. They become waste, they've expired, and that comes with huge financial and disposal costs.
So the model for concrete has to be forced to recognize a simple truth. The daily supply must be perfectly synchronized with the daily consumption.
Yes. You cannot rely on a fictional stockpile to handle a peak in demand. You're essentially programming a rule that says inventory accumulation is forbidden for this item. Getting that right is the difference between a successful project and just chaos.
Okay, let's really dig into that concrete example. The numbers really drive home how dangerous a flawed ontology can be.
It's the ideal case study because you can quantify the distortion that comes from one simple classification error.
So let's run the comparison. We've got a project that needs a certain amount of concrete, and the plant has a fixed daily production limit.
And we start with the mistake. Model 1. We treat the concrete as storable. The planner goes into the system and just incorrectly defines it as a standard inventory item.
So the RCPSP model just does what it's designed to do with inventory.
It does exactly that. It sees a production surplus. You made 100 units, used 50, and it faithfully rolls that leftover 50 into a fictional stock balance. The system, mathematically, believes you can start the next day with 150 available units.
And the schedule it produces looks amazing.
It looks perfect. The consumption curve is smooth, the system is balanced, and the schedule is fast because the algorithm can use this fake stockpile to cover high demand days.
But it's completely unexecutable.
Completely. That accumulated stock balance represents material that, in the real world, has spoiled. It's a pile of hardened waste. The planner has made a schedule that is mathematically sound but violates the laws of chemistry.
So now for the right way to do it. Model 2. Treating concrete as non-storable.
Now, the model respects perishability. The daily production limit is a hard, non-accumulating cap. If the daily capacity is 100 cubic meters, you can't use more than that, and any unused capacity is lost, gone.
And the algorithm has to deal with that reality.
It's forced to. It has to delay the next concrete-dependent activity until the capacity cycle renews the following day. It has no choice but to stretch the schedule out to match reality.
And this is where we see the real numbers, the true cost of that fantasy. If the simple CPM model, the one with infinite stock, gave us a completion date of, say, January 26, 2026.
The moment we impose the real-world, non-storable physics of concrete, that schedule is forced to shift. A lot. The true executable completion date moves out to around February 20th, 2026.
Wow, that's nearly a month. A 4-week delay caused entirely by the physics of one material.
And this is the critical insight. That delay isn't a sign of inefficiency. It's the necessary cost of removing the fantasy.
It's the price of reality.
It's the schedule finally acknowledging the world it actually operates in. If a planner tried to execute that January 26th schedule, they'd face 4 weeks of uncontrolled chaos, massive cost overruns from spoiled material, and constant bottlenecks, all from one bad classification.
And for anyone listening who manages projects, the histogram, the resource usage chart, gives this away visually, doesn't it?
It's the definitive tell. If you're looking at a chart for a non-storable resource like concrete, and you see a positive, growing inventory balance, a rising stock level, your model is fundamentally broken.
A positive balance isn't an advantage, it's a warning sign.
It's visual proof of predicted waste. For a correctly modeled resource, the consumption line should perfectly hug the capacity line. It should show that strict synchronization and the accumulated balance should never, ever roll over.
That's a powerful idea. The accumulation you see in the software is actually proof that your model is impossible.
Now, this is where we get to the most critical lesson, the one that really expands this whole concept.
Okay.
The idea of non-storable goes way beyond things that physically spoil. There are resources that don't decay at all, but they are still operationally non-storable.
So we're moving from chemistry to pure logistics constraints.
Yeah.
The time limit isn't about physical decay, it's about a window of opportunity closing.
That's it, exactly. Let's take a common but often misclassified resource. Physical space. A capacity resource.
This is a huge problem on crowded city construction sites or in complex factories.
Think about the daily availability of a critical assembly bay. Let's say it's got 100 square meters of certified floor space, and that capacity resets every morning at 8 a.m.
And yesterday, the team was slow, maybe some equipment broke down, and they only used 50 of those 100 square meters.
A planner using a flawed model might think, great, we have a surplus. If the model treats space like inventory, it rolls over that unused 50 square meters. The schedule might then calculate that for today, you have 150 square meters available.
And the scheduler, seeing that number, happily schedules a massive task that needs 140 square meters.
And that's the moment the project physically grinds to a halt. The space you didn't use yesterday doesn't become credit in the bank. Yesterday's opportunity vanished at 5 p.m. It renewed at 100 square meters this morning, and 140 square meter jobs simply will not fit.
The failure is immediate. The task is delayed, and now you have expensive labor and equipment standing around for a job that physically cannot be done.
Right. And you paid for the full 100-meter match order yesterday, but you gain no future advantage from failing to use it. That's a pure financial loss. The RCPSP model has to be told that space capacity is non-accumulating.
So we're not tracking material anymore. We're tracking the time-bound permission to use a resource at a certain level.
You've nailed it. Which brings us to the most abstract, but maybe the most impactful category of non-storable resource. Operational authorizations or permissions.
The bureaucratic hurdles.
Exactly. Access permits, utility shutdown windows, crane operation clearances, the administrative keys that unlock execution.
They don't spoil, but they have rigid time boundaries.
Think about a project in a busy city. You get a permit to close a traffic lane from 9 a.m. to 3 p.m. Yesterday, your crew finished early and only used 3 hours of that 6-hour window.
Those other 3 hours don't get added to today's permit.
Never. The permit doesn't say 60 hours of closure this week. It says 6 hours today. The right to use that time expired at 3 p.m. yesterday. But if your RCPSP model allows for the stocking of these authorizations, the schedule it produces will be mathematically balanced.
But administratively and legally impossible.
Utterly unviable. The crew shows up today relying on the 5 permit hours the schedule says they have saved up, only to find out they have a new 3-hour window, and that's it.
The planner has just created a guaranteed delay.
Yes. The crew is idled, the foreman is on the phone begging for an extension that probably won't come, and it all goes back to that initial human decision about the resource's nature. It's about defining the operational physics of the project.
And if those physics are wrong, the most sophisticated algorithm in the world will still give you a failed project.
It will just calculate the failure with much higher precision.
Okay, so now that we have these two classes of resources, let's talk about the planning logic. It sounds like you need two completely different mindsets.
You absolutely do. For storable materials, the logic is all about flexibility. It's about inventory management. This is where RCPSP is brilliant at optimizing buffer stocks.
You gain control by accumulating things.
Exactly. We can level out consumption. We can order materials way in advance to manage long lead times. We can build up inventory buffers to absorb shocks in the supply chain. It's all about smoothing things out.
But when we switch to non-storable resources, that logic completely flips. You can't buffer volatility with inventory. You have to buffer it with time.
The logic for non-storables is 100% about strict synchronization. The planner's entire focus has to be on making sure capacity and consumption align perfectly in that time window. You have to actively tell the software not to carry over surpluses.
So for concrete, you're synchronizing the crew's speed to the plant's delivery rate. For physical space, you're synchronizing the number of jobs to the fixed area.
And that defines the core duty of a modern planner. It's governing that resource classification list, going through it line by line and asking, is it storable? If not, is it perishable, like concrete, or is it operational, like a crane?
And what happens if you misclassify a crane's time, which is a non-storable capacity resource, as storable?
The model, in its quest for the shortest schedule, will see that the crane was only used for 6 hours yesterday, and will try to schedule a 10-hour shift for it today, using those 2 accumulated hours.
But in reality, the crane crew goes home after 8 hours.
Right. And their unused time doesn't magically become free overtime the next day. So the methodological lesson holds true. RCPSP only works when it converts those fake implicit assumptions into explicit, correctly classified constraints.
If the classification itself is wrong, you just used a very powerful tool to calculate an optimized failure.
You've just moved the error from a vague assumption to a high-precision calculation. The result in the field is exactly the same: failure.
This brings us to the tools of the trade. Planners live and die by their software. It sounds like there's a big clash between this theory and what most software can actually do.
This is a huge friction point in the industry. Your traditional off-the-shelf project management software really struggles to enforce this kind of synchronization logic without a lot of manual fighting.
So when we say traditional tools, we're talking about the big names, right? MS Project, Primavera.
Right.
What's their structural limitation here?
Historically, those platforms were built to do 2 things really well: activity sequencing, your basic CPM logic, and managing people, so labor leveling. And labor is a non-storable capacity, which is fairly simple. You can't save up a worker's unused hour from yesterday.
Sure.
The problem comes when those tools handle material resources. Their default logic, their DNA, is inventory management. They assume accumulation is the norm.
So if I put 100 units of space capacity per day into MS Project, it's probably going to treat it like a pile of widgets by default.
It's very likely to. If 50 units go unused, it'll try to accrue them. The core logic just isn't built for the rigid synchronization needed for permits or space or perishable concrete. To stop it, the planner has to resort to these really cumbersome manual workarounds.
And what does a workaround like that even look like? Why is it so bad?
Oh, it's messy. You might have to create fake resources, like a concrete delivery slot instead of concrete, and then manually set its availability to reset every day. Or you create a web of artificial dependencies that block activities, which completely defeats the purpose of letting the RCPSP engine optimize for you.
You're basically turning an automated calculation into this delicate, hand-built model that you have to constantly watch over.
Precisely. The efficiency you were supposed to gain from the software is lost in the complexity of managing the workarounds. You're fighting the tool's basic assumptions, and that just opens the door for more errors.
So to do this properly, especially for those abstract capacity and conditional resources, you need specialized tools. Tools that were built with this kind of classification in mind from the ground up.
That is the key differentiator. You need a system that understands the nuance between storable inventory, perishable goods, and non-storable capacity.
Which brings us to the tool that our deep dive highlighted for this specific capability, Spider Project. What does a tool like that do differently? What's the structural feature that lets it avoid this accumulation default?
Spider Project was designed with this resource ontology at its core. When you define a resource, you don't just give it a quantity, you define its inherent nature. It has explicit classifications that let you tell the system this material is perishable or this capacity is non-accumulating.
So when the scheduling engine calculates a surplus of that perishable concrete, it doesn't just roll it over.
It can't. The software enforces the rule internally. For non-storable resources, it knows that any unused capacity is just a lost opportunity and writes it off. For perishables, it understands the time decay factor natively. It forces the synchronization and stretches the schedule to reflect reality all on its own.
It prevents the error by design instead of forcing the planner to fight the default settings.
And that's what allows the RCPST model to finally do its job. Calculate the fastest possible timeline within the parameters of defined reality.
Which brings us right back around to that golden rule, which has to be the first step in any resource plan.
It's the simple objective test. The planner has to ask this one binary question for every single resource on their list. Can this resource be stored and used later without any loss or without accumulating the right to use?
If the answer is yes, for steel, for wiring, for bulk materials,
then your stock balance logic is valid. Model it as storable. Use that inventory as a buffer. Use it for flexibility.
But if the answer is NO, for fresh concrete, daily permits, crane time, floor space,
then it is non-storable, and the model must enforce strict synchronization. You have to prevent accumulation, whether it's because the resource spoils or because the opportunity expires. You are consciously trading that imaginary fastest possible schedule for one that is guaranteed to be viable.
The ultimate lesson here is that getting the ontology right isn't a technical detail. It's the most fundamental strategic decision a planner can make. Well, this deep dive has really shown the critical difference between a beautiful simulation and, well, logistical reality. We've gone beyond the simple math of a schedule and into the physics of materials and capacity.
We've confirmed that the most important moment in project planning isn't when you click calculate. It's that initial human decision, when you define reality for the tool.
And we saw the real cost of that error with a concrete example, a 4-week delay hidden inside a single flawed assumption.
Which leads us to our final thought for you, our listener, to take away. If just respecting the physics of a common material like concrete demands a 4-week extension to your timeline, what other implicit, unexamined assumptions are hiding in your project plans right now?
That's a great question.
Are you diligently classifying your crucial capacity resources, your clean room access, your specialized equipment windows, your regulatory inspection slots as non-storable? Or are you, right now, relying on accumulated fictional stock balances that will guarantee that the beautiful schedule you're about to present is fundamentally impossible to execute?
It's time to go audit those resource classification lists. Thank you for joining us on this deep dive into project physics.
Go define your reality, and we'll see you next time.